China has decisively cut ties with ASML and TSMC, ending all procurement contracts for ASML's lithography systems and TSMC chip orders through state-linked firms as of April 12, 2025. This abrupt severance marks what Bernstein analysts describe as the most significant shift in semiconductor sovereignty since 1987. The backdrop to this move is China's aggressive buildup of local fabs, with SMIC boosting its deep ultraviolet DUV production capacity to over 300,000 wafers per month, effectively doubling output compared to 2023 per IC Insights data. For ASML, whose EUV lithography systems generate nearly 70% of gross margin, the consequences were immediate and severe. UBS analysts noted a 12% decline in advanced tool bookings from Asia during the first quarter of 2025. TSMC faces a complex strategic crossroads. Its $100 billion U.S. expansion project, once hailed as a geopolitical victory by Washington, has become a liability as Beijing blacklists all nodes beyond 7 nanometers. The shock, however, isn't China's withdrawal. It's the preparedness behind it. The alternative China has built threatens to render Western sanctions ineffective, like old scaffolding on a tower that no longer requires support. When Washington enacted sweeping restrictions against Huawei in 2020, cutting off access to TSMC's advanced nodes and ASML's EUV technology, it initiated, as Credit Suisse called it, the most costly forced innovation cycle in modern tech history. Within 5 years, Huawei and SMIC retaliated with the Mate 70 Pro, powered by a domestically manufactured 7nm chip made using DUV lithography, combined with self-aligned quadruple patterning SAQP. This chip was created without foreign tools or imported wafers. An analysis by Tech Insights in February 2025 revealed a transistor density only 17% lower than Apple's A17 Pro chip, but functionally competitive, especially on AI inference benchmarks. Following this, Huawei's Ascend 910C, designed to compete with NVIDIA's H100, entered mass production in March 2025 at Huawei's Qingpu plant. Bloomberg reported over 30 domestic AI companies inked supply agreements with Huawei in the second quarter alone. This was not a mere workaround. It represented an architectural inversion of the chip-making landscape. If China's subsequent steps succeed, it will shift from catching up to setting the pace in the semiconductor race. SMIC's stealth attempt to produce 3nm chips without EUV technology has divided expert opinion. On one hand, TrendForce analysts argue that achieving commercial yields at 3nm without EUV is nearly impossible due to the immense complexity of multi-patterning. On the other hand, teardown data from a leaked SMIC prototype wafer in April 2025 showed critical dimension shrinkage to 34 nm gates, approaching 3nm scale, achieved through quadruple patterning. While production costs and times nearly tripled, and wafer yields lingered around 40%, according to IC Lab Asia, Beijing's goal isn't Western-style efficiency. Instead, it's volume and resilience. With state subsidies absorbing losses and assured demand from domestic AI and defense projects, SMIC's strategy is not about capitalist economics, but geopolitical precision. Morgan Stanley's March 2025 report warned that China doesn't need to match TSMC's cost structure. It only needs to rapidly scale a minimally viable alternative before sanctions can disrupt it. NVIDIA's withdrawal from China's AI market in late 2024, caused by US bans on its H100, H20, and B200 chips, left a $7 billion vacuum. Huawei capitalized immediately, beginning mass shipments in May 2025 of the Ascend 910C. This chip, engineered by combining two 910B dies in a 2.5D package, rivals NVIDIA's tensor processing capabilities. Although it's not a monolithic 5nm breakthrough, the design achieves 75% of H100's performance at roughly 55% of the cost, as reported by China AI Tech Watch. Huawei sold out its initial batch to state-backed cloud providers within 11 days. More crucially, SMIC's production line, leveraging DUV lithography with enhanced SAQP, raised its wafer yield rate to 56% by mid-May, a significant improvement from 31% in January. This isn't a story of pure technical parity but of strategic asymmetry. Huawei doesn't have to outperform NVIDIA on every metric. It just needs to supply chips that are good enough and delivered on schedule. The AI arms race has opened a new front, one that no longer centers on Silicon Valley. By the second quarter of 2025, over 82% of components used in China's sub-10 nm chip manufacturing were domestically sourced, according to the China Semiconductor Industry Association. SMIC's new megafab in Shenzhen, built in a record 16 months, now produces 45,000 7nm class wafers monthly. Meanwhile, Shanghai Microelectronics Equipment, SME, achieved its first production run of 28nm capable steppers in March, and is targeting 14 nm production by late 2026. The tectonic shifts in China's semiconductor landscape are clear. It's not just about supply chain independence, but about rewriting the rules of the semiconductor race. This transformation threatens to redefine the global chip industry's balance of power for years to come. Since 2022, over 1,500 top engineers from industry giants TSMC and UMC have reportedly accepted multi-year contracts to work for mainland Chinese semiconductor firms, attracted by compensation packages that are on average 2.3 times higher than what they earned previously. This massive talent migration signals a strategic shift in the semiconductor landscape, fueled by Beijing's $47 billion chip fund, which was restructured in 2024 under the oversight of the State-Owned Asset Supervision and Administration Commission, SASC. The fund's renewed focus prioritizes vertical integration within China's semiconductor ecosystem, rather than continuing to rely on global interdependence. Unlike industry leaders like ASML, which depend heavily on specialized suppliers such as Carl Zeiss Optics and German photonics companies for key lithography components, China is deliberately cultivating a self-sufficient and methodically converging domestic ecosystem. If this momentum holds, the greatest threat to Western chip dominance won't be covert espionage or intellectual property leakage. It will be obsolescence brought on by strategic redundancy. The West risks becoming irrelevant simply because China builds alternative capabilities that bypass existing choke points. In February 2025, semiconductor analysts were stunned by a leaked engineering document from China's State Key Laboratory of Laser Technology. The document revealed a prototype blueprint for a revolutionary EUV source technology called laser-induced discharge plasma, LDP. This new design promises to reduce power consumption by up to 90%, compared to the established ASML laser-produced plasma, LPP, EUV sources, which currently power most advanced lithography machines globally. According to research published in the E-Journal of Photonics, the traditional ASML system relies on a complex twin laser mechanism that vaporizes tin droplets, yet converts less than 0.1% of input energy into usable extreme ultraviolet, EUV light. In contrast, the Chinese LDP approach uses a staged dual input method. It first employs a low-power ionizing laser to trigger plasma generation, followed by a high-current electrical discharge that sustains stable EUV emission. Early laboratory tests by engineers at Applied Optics Beijing reported producing EUV light at the critical 13.5 nanometer wavelength with an efficiency rate between 0.8% and 8%. A staggering improvement that's approximately 8 times more efficient than current Western systems. Although these results are promising, the challenge remains to prove durability and stability under high-volume fab-scale throughput conditions. The implications are enormous. If scaled successfully, the LDP technology could eliminate reliance on ASML's $170 million EUV lithography units, which currently consume over 1 megawatt of power each. This single leaked blueprint has already shifted global investment narratives about the future of semiconductor manufacturing. But the big question remains: how close is China to turning this theoretical design into an operational machine on the factory floor? ASML's current EUV supremacy is built on a manufacturing process that ironically consumes more energy than the wafers it prints. According to data from the International Energy Agency, a fully operational EUV production line draws the equivalent power of approximately 1,200 average American homes every month. The LPP method employed by ASML demands an ultra-high repetition rate of 50,000 laser pulses per second, supported by extensive heat mitigation infrastructure and intricate mirror arrays that degrade rapidly, typically after processing just 20,000 wafers. By comparison, China's proposed LDP system bypasses the entire tin vaporization step, instead generating stable plasma via an electrical discharge that emits EUV light with a thermal load close to ambient temperature. Chen Wei, a former engineer at Zeiss SMT now consulting for Asia Lith, told Bloomberg that if the LDP approach proves scalable at an industrial level, it could shatter the long-standing trade-off between precision and energy consumption that has defined EUV lithography for over 15 years. ASML declined to comment publicly, but in April 2025, it quietly cut its EUV shipment forecast for the year by 18%, citing regional procurement uncertainties. Simultaneously, the company has begun quietly redesigning its next-generation EUV source architecture, signaling an urgent strategic pivot driven by tangible competitive pressure. Meanwhile, TSMC's highly anticipated 2025 Arizona fab project is more than just an expensive manufacturing facility. It's geopolitically vulnerable. Backed by $6 billion in U.S. subsidies and bound by joint production agreements tied to American national security directives, TSMC must now balance commercial imperatives against Washington's strategic priorities. This dynamic has turned TSMC's operations into a de facto extension of U.S. geopolitical strategy, complicating the company's traditionally market-driven decisions. ASML, whose core optical components depend on German export licenses and Japanese photonics technologies, finds itself caught in a complex triangulation between Dutch regulatory frameworks, American political pressure, and loss of Asian customers, especially in China. This tension is reflected in TSMC's foundry utilization rate, which dropped to 76% in the first quarter of 2025 from 89% during the same period in 2024, largely attributed to Chinese contract cancellations, according to semiconductor market tracker TrendForce. At the same time, Canon's newly commercialized FPA 1200 NZ-Z2C Deep Ultraviolet (DUV) lithography system has gained unexpected market traction as a geopolitically neutral alternative, shipping 27 units to Southeast Asia in the past 5 months. While ASML's dominance remains intact, its protective moat is visibly eroding. The bigger issue for Dutch optics manufacturers and Taiwanese wafer fabs isn't just that China has walked away from the table, it's that other players are now filling the void left behind. That said, it's crucial to recognize that building a prototype EUV system is vastly different from operating a reliable machine capable of running 30,000 wafers per month at 95% uptime. China's LDP project still faces formidable technical challenges, including manufacturing ultra-high reflectivity mirrors consisting of over 100 molybdenum silicon multilayers, each requiring defect tolerances below 0.2 nanometers. Executives at Tokyo Electron told Nikkei Asia in April 2025 that China's in-house metrology tools continue to struggle with sub-angstrom calibration precision necessary for accurate mask alignment during lithography. Meanwhile, domestic photoresist manufacturers such as Giwa Chemical have yet to develop EUV-compatible polymers that meet stringent yield variation thresholds required for mass fab deployment. Even if the LDP EUV source functions reliably, synchronizing throughput across etching, deposition, and inspection stages of the semiconductor manufacturing process remains a critical, unsolved integration hurdle. China's State Council recently allocated $9.3 billion in funding across 4 pilot production lines, signaling strong government commitment to the goal. But the country still lacks industrial readiness. Lisa Chow, tech strategist at Bernstein, summarized the situation succinctly. China has demonstrated proof of concept. What it lacks is repeatability and reliability under industrial pressure. But that gap can close quickly. Just ask anyone who once believed Huawei would never produce a 7-nanometer chip. The reality is clear. If China manages to sever dependencies on ASML and TSMC, and instead build a lithography ecosystem that is leaner, cheaper, and dramatically more energy efficient, it will fundamentally reshape the global technology stack. Every AI server, every quantum computing simulation, and every next-generation military targeting system over the next decade will depend on which nation controls the EUV light source at the heart of chip manufacturing. Right now, ASML holds that critical control. But what if Beijing has already cracked the fundamental technology? The leaked blueprint may only